Thank you, Eric. By now you should be exhausted. I believe this presentation will not be so tiring. This is a joint work with Aviram Rojas Moreno. And yesterday we heard about cryptology. Today a little bit about coding theory, but don't ask me too much about coding theory. Not an expert in it. So a little introduction about cross products. First, group graded rings. An associative ring A is graded by a group G if it admits this decomposition as an abelian group, as a direct sum of AG. And the product satisfies AG times AH lies inside AGH for every G and H in G. The abelian group AG is termed the G's homogeneous component of A. And the multiplicative condition yields that the E component, where E is the trivial element of G, so the E component AE is a ring termed the base ring of A, and that the decomposition is not only of abelian groups, but it decomposes A as an AE bimodule. There are a few ways to define equivalence of graded rings in such a way that respects their gradings. A graded equivalence, this is one of those, which is important to me now in this talk. A graded equivalence between two graded rings is a pair psi phi, where psi is a ring isomorphism between A and B. Phi is a group isomorphism such that psi of the G's homogeneous component of A is exactly the phi of G component of B for every G. Is natural. A graded ring is a cross product if there is an invertible homogeneous element for every G in G, say UG in AG. In this case, the homogeneous component AG is just this UG, the invertible element, times AE, either from the left or from the right. And hence we can write A as this direct sum, AE UG, over all G in G. Let the base ring, call it R, AE is R, then we usually write a cross product as R star G as a direct sum of R UG, G runs over all G's. And any element of R star G is uniquely written as the sum of a beta G UG with a uniquely determined coefficient BG in R. Suppose now, from now on, the base ring would be commutative. What is the structure of a cross product over commutative rings? This is well known. Since the cross product respects the G grading, that is RUG, RUH is exactly RUGH for every G and H in G, then R star G determines a G action on the base ring R via the rule G acts on R by conjugation by UG. And it doesn't depend on the choice of invertible homogeneous elements. The same equation gives rise to a two-place function taking G and H to UG, UH, UGH inverse. This does depend on the choice of homogeneous elements. And the image lies in R star, the multiplic group of units of R. Associativity of R star G yields that F is a two cocycle. To keep the action and the cocycle in mind, we denote the corresponding cross product by, not just by R star G, we write R F eta star G. And the cohomology, we will write the action eta, we'll write it as a subindex. Certain cross products draw special attention when the G module structure, by the way, the cocycle here, the R is endowed with a eta as a module over G by the action eta. So for every eta, there's a different cocycle group. Certain cross product draws special attention. When the G module structure on the base ring R is trivial, in other words, R is central in R star G, then the cross product is written RF star G, and it's called a twisted group ring. On the other hand, when the two cocycle is identically 1, the corresponding cross product R1 eta star G is called a skew group ring. A skew group ring, which is also a twisted group ring, is just an ordinary group ring RG. No cocycle and no action. An important family of cross product arises when R is a field and eta is a Galois action admitting a fixed field K. In this case, the corresponding cross product is K central simple and is called a classical cross product. It has a key role in the Brouwer theory. When the group is cyclic, let's concentrate for a moment on cyclic cross products. When G is a cyclic group of order n, a cross product R eta F star Cn is isomorphic to a quotient of the skew polynomial ring. It's Ry eta, where Y acts on R via the automorphism eta of sigma. And the quotient is by the ideal generated by Y to the n minus beta, where beta is an eta invariant unit in R. Okay, please ask if there are any questions. Let R be, okay, so that was, I think most of you know what was so far. Let us talk a little bit about coding theory. Let R be a commutative ring with 1. An R linear code of length n is an R sublattice of the free R module R to the n, called the ambient space. Yesterday, Carlo called it the text space. Call it the ambient space. A code W of length n is cyclic if it is invariant to cycles, meaning that if x1, x2 to xn is in the code, then so is xn, x1, and so on to xn minus 1. These are very, very well-studied codes, cyclic codes. More generally, W is beta constacyclic for some invertible element beta if, in addition to the cycle, we add to the first component this beta. This is also well-studied. These are also well-studied codes. As can easily be verified, constacyclic codes are ideals in the twisted group ring Ry over y to the n minus beta. This is the same beta. Here we don't have a skew polynomial ring because we do not have an action. This is very easily verified. More general families, namely group codes, skew constacyclic codes, and classical cross-product codes have been well studied and shown to yield good parameters, whatever that means in coding theory. I can tell you a little bit about it if I have time. Although not always explicitly represented in this way, all of those are ideals of certain cross products R star G, which are lattices over R. The length of such codes is the cardinality of G, and their rank as free R modules is often denoted as their dimension. Let B be an R base. Now take any R linear code, and let B be an R basis of an R lattice M. We say that the pair MB is a based R lattice. Such a based R lattice determines a Hamming weight, which takes any element. It is uniquely written as a sum of its base elements with coefficients. You just and its Hamming weight is just the number of coefficients of base elements such that their coefficients are non-zero. This in turn furnishes M with a metric space structure. Note that the unit sphere in this metric space is the set of non-zero monomials, Rb, where B is any base element and R is any element in R. The quality of a code, here is something where I said good parameters. The quality of a code given as a sublattice of a based R-lattice is measured by the minimal Hamming distance between its elements. Okay, you don't want two code elements to be too close. And also by its length and rank, but we are interested in the Hamming distance. An isometry between two based R-lattices, M and M prime, is defined to be an invertible R-module morphism from M to M prime, which satisfies this compatibility equation, comparing the Hamming distances in M and M prime via O, for every M in M. This is natural, of course. Based lattices are called isometric if such an isometry does exist. Okay, if we have an isometry between two spaces, then such space can be isometrically mapped to itself. We say that an R-module automorphism is an isometry if this if condition 7 holds. Skip that. An isometry between two based lattices maps the unit sphere of one space into the unit sphere of the other, hence yields a unique bijection between the bases, B and B prime, in such a way that rho of B is some RB, some coefficient RB times rho prime of B, or some RB in R star. Rho prime is determined by rho. In fact, a bijection of invertible coefficients, given a bijection, condition 8 is also sufficient for an R-module morphism to be an isometry. This is easy. Clearly, isometric lattices have the same rank. Denote the base element by Bi and Bi prime. Then the bijection determines a permutation in the symmetric group sigma n on n elements. By the equation above, the group of isometries of a based R-lattice of rank n is generated by two subgroups, namely the above symmetry group and the group of invertible diagonal isometries given by R tuples, RB1 until RBn in R star n, R star to the n, with the identity permutation. More precisely, the group of isometries of this R lattice is, this should be not gamma n of R, it's gamma n of M, of MB, is the Ritz product of R star and sigma n, where sigma n acts on the n tuples of R star by permutations. This is just the monomial group of the lattice. As shown above for constacyclic groups and all the cross product codes, constacyclic codes, and more generally for cross product codes, an R lattice M can be equipped with an additional ring structure, admitting R as a subring. In this case, a code in the ambient space is usually considered as an ideal M, which is also an R sublattice, as we saw in the above cases. But more generally, coding theorists reduce the number of codes by taking only ideals and not just R lattices. An isometry of based R lattices rings is defined to be based R lattices isometry, which is also a morphism of rings. We add this condition. Okay, what is special in cross products? cross products ambient spaces are regarded as based R-lattices implicitly with G-graded bases of units, UG, G in G. You just pick any R basis of units, your favorite one. The corresponding Hamming weight is just taking this sum, sigma beta G UG, to the number of group elements which admit non-zero coefficient. It is not hard to verify that an isometry between two cross products, in this sense, of G is nothing but a G-graded equivalence as defined above. Distinct choices, okay, so what is the motivation here? Distinct choices of an algebra structure and basis without which one cannot have a Hamming distance may essentially yield the same codes. This was remarked by Dean in 2008. He gave an example of algebraic isometry between two base lattices, one which determines certain negacyclic codes. This is what they call a constacyclic code, where the corresponding beta is -1, while the other determines certain cyclic codes. So sometimes negacyclic codes may be cyclic codes. So he just remarked it and without any classification. It is therefore natural to mod out ambient code spaces by the isometry equivalent relation. And here is the problem. Let G be a group, R a commutative ring. G is finite, of course, R a commutative ring, and eta is an action. Eta is an action of G on R. Determine the Hamming isometric classes are eta F star G over the two cocycles in this cocycle group. So you have to partition this cocycle group according to the Hamming isometry. Okay, this is a lemma. There is a subset of automorphisms of G which are compatible with eta. The automorphisms of G such that eta composed with these isometries is again eta. This set is a subgroup. It's not just a set, it's a subgroup of automorphisms of G which admits a natural action on the corresponding cohomology group, H eta to G R star. So when we have a group of cocycles, we mod out by the group of coboundaries, we get the cohomology group, and on this group, this group of compatible automorphism is well defined. We have, the theorem is as follows: two cross products with the same group G, same group R, same action, different two cocycle. They are isometric, or in other words, graded equivalent with as R modules. If and only if the homology classes of F and F prime belong to the same orbit under this action of ot eta G on the cohomology group. In other words, fixing an action eta, the Hamming isometry classes of cross products are eta F star G are in one-to-one correspondence with this quotient set, H2 over the compatible automorphisms. The group of isometries of a cross product is a subgroup of the monomial group. Okay, so the monomial group is blind to the product, just as an R-lattice gives us isometries. This is the monomial group. It is gamma of the order of G R, which we saw. This is the Ritz product, or the semi-direct product of R star to the power of the order of G with the symmetric group of size G, generated by the R star to the power of the order of G and by the subgroup of a subgroup of the symmetric group as follows. the group of diagonal isometries does not change the cohomology class. That is, it yields cross products such that the cocycles are cohomologous. So this is even a more fine equivalence called graded isomorphism, not just graded equivalence. But here we have another part, the permutations in the symmetric group, which take care of the multiplicative property of the isometries, which correspond to the compatible are the elements of OT eta G. OT eta G is a subgroup of the symmetric group. Corollary, this is the isometry group of cross product is just R star to the G, and instead of taking the semi-direct product with all the symmetric group, we take the compatible automorphisms. So this is the isometry group. Okay, this is general, and now we come to the more arithmetic part, which is how can we classify cyclic cross products over finite fields. So this in the literature, sometimes you see that they do the same work over and over, and actually yielding the same codes. We call it in different ways. So there is a need in somehow to make an order in this mess. Okay, in this case, we have a cyclic group, Cn, generated by sigma, a finite field. Okay, finite field, this is the most usual base ring that people take in coding theory. Finite field of size q to the r, where q is a prime number. An action, Cn, to the automorphism of this finite field, taking it is determined by the generator sigma. It goes to some power of the Frobenius automorphism, which generates, as you all know, generates the automorphisms of this finite field. Is of order R, Frobenius. So sigma goes to some phi to the k, and we may assume that k up to isometry, we can assume that k is a divisor of R. The action can be classified by the divisors of R. What trivial action is when you take k to be R itself. Okay, so the answer should be the answer of classification of these cyclic cross products according to Hamming isometry should be a function, should be dependent on 4 parameters, n, q, r, and k, with the demand that k is a divisor of R. So we need to have an action depending on this quadruple. So firstly, the size of the corresponding cohomology of Cn with the coefficients in the units of this finite field is of order which is the greatest common divisor of the size of q to the k minus 1, where k is determined by the action, and nk divided by R. Nk over R it turns out to be an integer. So the GCD is just the size of the cohomology, and now we have to partition this cohomology with respect to the isometry. Define an equivalence relation which depends on eta on this set. A set of non-negative integers lesser or equal to m. 2 elements are in this set are equivalent if there exists an integer j such that aj is congruent modulo m to b, and such that J is coprime to n and is congruent to 1 mod R to the k. We call that R over k is an integer. So this is the condition. It's a bit complicated, but we have a theorem. So let eta be an action of the cyclic group Cn on the finite field fq to the r. Then there is a one-to-one correspondence between the Hamming isometry classes of the cross products and the quotient set of 1 to the m with respect to this equivalence condition. So you see all the ingredients are here, n, k, q, and r appear here. Okay. What about the special case of a constacyclic ambient spaces? Constacyclic, meaning eta is trivial, meaning k is just r. So this condition is trivially satisfied, and this is just n. K over r is 1, so this is just n. So in this particular case, a consequence of the above theorem for trivial eta reestablishes a result of Chen, Fan, Lin, and Liu from 2012 for constacyclic codes. So the action is trivial, and the corollary is that the Hamming isometry classes of ambient space of fq to the r constacyclic codes of length n, namely the twisted group algebras fq to the r f star cn, are in one-to-one correspondence with a set of divisors of the size of the cohomology class, which is just the greatest common divisor of q to the r minus 1 and n. As another consequence, we can determine when negacyclic codes of length n over a field fq to the r are essentially cyclic. Remember that I told you that in 2008, they found that negacyclic codes may essentially be cyclic. In order to formulate an answer in arithmetic terms, we decompose the integers n and the integer q to the r minus 1, which is the, so this should be fq to the r star, to their two-part and odd part. That is, q to the r minus 1 is 2 to the L1 times M1, and n is 2 to the L2 times M2, where M1 and M2 are odd. So we decompose it to the two-part and to the odd part. And the theorem is as follows. Negacyclic codes of length n over the field fq to the r are essentially cyclic if and only if either q is 2, and then it is okay. This is trivial because 1 is minus 1. There's no problem in that. But it also happens for odd primes. If q is an odd prime, then what we just need is L1 to be greater than L2. And then we get that there's no essential difference between negacyclic codes and cyclic codes in the isometric way of speaking. Okay, so that's it. Thank you very much.